Okay, so welcome back to the second module of the course which we have started in last to last lecture, which was powder processing. So we are looking at powder processing, and we have already introduced you to the various concepts and applications of powder processing, and we also started with characterization of powder. Now in the characterization of powder, we looked at the size range, and you saw that what is the usual size range for powder is. Next we want to look at the characterization of powders. How do we characterize them? And in that context, we found that shape and morphology of the powder particles can be very wide and very different. It can be as simple as spherical, angular, rounded, teardrop, porous sponge, and you name it and you have a shape over there. So there are various kinds of shape that is possible there. So it is difficult to quantify, whether you are talking about quantifying the volume, surface area, or anything. So individual particle basis you cannot quantify, and not only that, there may be even variation in one set of powder. So for example, even on a general note, what you will see is that all the particles may still be spherical, because it will depend on what particular process you are obtaining the powder particles. But even in the spherical range, you would see that diameter varies. There may be some amount of ellipsometry. It may not be perfectly spherical. Obviously it cannot be perfectly spherical. That would be art and not science. So there can be wide variation, and therefore we need some way to characterize some of the important parameters like area, volume, and so on. So we will look into that. How do we do that? Now these shape and morphology of the powders depend mainly on what particular process of production has been used. For example, atomization on an average will always produce spherical particle. On the other hand, electrolytic process will produce something like a spongy or dendritic particles. So the powder shape and morphology is greatly determined by the process that you use. It is also influenced by the energy of the crystal facets. For example, some of the crystal facets may be very slow growing, and therefore they will be overcome by the other faster growing planes, and in that case you would see some faceted structure. So the crystal phases of energy of the crystal facets also influences the shape and morphology, and these shape influences some of the powder characteristics. For example, flowability, compatibility, and agglomeration. So even though the average diameter to determine or to define the powders of a spherical size may be same as that for say a spongy or the dendritic kind of powder, but their flowability, compatibility, compactability, actually it is not compatibility, compactability, how much you can compact, and agglomeration characteristics can wide in range. So you have to understand that there is always going to be some inherent variation in the shape and morphology. Now we also saw that we can define, or we can basically classify them in different classes. For example, you can say one dimensional, two dimensional, and three dimensional. So for example, acicular or rod like or elongated ligament kind can be put as one dimensional. Then in two dimensional it will be flake type or dendritic type, which does not have very large dimension in the third dimension, and then most of the other shapes will fall in the three dimensional category. However, whatever be the shape and size, we are always interested in calculating an effective diameter. Now that effective diameter that you calculate or you want to, that will define the size of the particle that you have obtained, will depend on what is your method of measurement. For example, if you have the image, let us say you have obtained some SEM images or micrographs, and from there you are trying to calculate the diameter size, then what you are actually looking at is only the projected area, and therefore you convert that projected area into the equivalent spherical particle, and then calculate what is the diameter of that equivalent diameter. Similarly, if there is a mechanism or there is a technique by which you are actually calculating the overall surface area, then again what you say is that I will find a diameter of a sphere which has equivalent surface area, and that is the diameter that you will say. Similar, and the other one, which is the most simplest one, is if you are some way able to calculate the volume, then that will give you the usual pi d q by c. and that will be your equivalent D. So, you can see how these are obtained, and if you are not, let me just quickly show it on the board on how exactly these equations come into picture. So, for example, let us say you have a projected area. So, what you are saying is that you know the area, projected area, from some technique, most likely some imaging technique, and you say what is the equivalent diameter dA which will have of a sphere which will have equivalent area. So, that will be pi dA square by 4, implies in this case if you knew the area, then the dA equivalent which determines or defines this size would be given by 4a by pi square under root. So, this is one definition of diameter. Similarly, if you are able to calculate the volume, which is the easiest one in terms of theory, but when it comes to technique or actual characterization, this may be very difficult. So, pi dV cube by C implies dV is equal to 6V by pi cube root of this. And if you know the surface area, there are of course techniques. In fact, this is the most common technique where you calculate the surface area. So, you calculate the surface area and then say what is the diameter which has the equivalent diameter. So, a spherical particle of diameter ds will have surface area equal to pi ds square, and you are saying pi ds square is equal to s, and therefore, the equivalent diameter for this is under root s by pi. So, these are different definitions. Now, you can see that even though your particles may have similar d value, but it need not always represent the same particle size or shape or even volume, because it depends on how you are calculating. So, for example, let us say you have calculated ds and dA for two different sets of particles. One of them you have calculated based on projected area, other you have calculated based on surface area. So, although these two are same, but if you were to calculate the volume, it may come out different, and in most of the cases that is how it will be the case. So, that is the particle size measurement. So, depending on the technique, you will have different equivalent spherical diameter. So, now that is one particle, but in general you will not get just one particle. You will have, you remember we had even the largest powder size, if we take, we have 10 to the power 9 particles per kg. So, that is the kind of number of particle that we are looking at. So, you will, and all of these cannot have exactly the same diameter. So, there will be some variation, and that distribution is what we need to understand. So, particle distribution, size distribution is given in terms of a histogram or a frequency plot showing the amount and number of particles in each size increment. So, on the x axis you will have increasing size. So, you will have different diameters in the increasing order, and corresponding to that, for a small increment you will find what is the frequency or the total number, and then you will plot it. So, this kind of frequency plot or the histogram is what will define the particle size distribution. If it were a perfectly uniform sized distribution, then you would get a straight line, and then you can imagine that is obviously not ideal case. In most in fact I should say 100% of the cases that is not what you will get. You will get a distribution, and that distribution needs to be defined in terms of some parameters, and the most usual parameters are mean, median and mode. So, what are mean, median and mode? Mean, most of you would be aware, mean is given by so if you have n number of particles, then mean would be given by, where yi is the frequency of the particle of this size. So, let us say di is some diameter, then the number of particles in that of that particular size. So, this is the frequency, and I equal to 1 to n. So, these are the different number of diameter, and so you divide by 1 over n, and this will give you the mean. Median would be d50, meaning the particle whose diameter is exactly at the 50th percentile. So, if you were to calculate or put the size in ascending order, then the particle, and there are, say, let us say 100, or to make it even simpler, let us say there are 200 particles, then the 100 or the 101st, depending on it is odd number or even number of particles, the diameter of the 100th or the 101st particle would define D50, and that will be the median. And another one is mode. So, mode is nothing but the diameter at the peak. So, if you were to plot the distribution, so let us say this is frequency, this is diameter, and this is how you are getting. So, whichever is the diameter just at the peak, this is the mode. So, these are the usual statistical terms you must be familiar with, but just for sake of completion I am putting it over here, and that will define your the different kinds of ways to define the distribution or to represent that distribution. But this is just one number, and it is quite possible that two different distribution may have the same mean or median values, and still they may have different distribution. Therefore, something else is needed to describe this distribution, and that particular quantity which is very common to describe this is standard deviation. So, for any kind of distribution you would like to have a standard deviation defined, and it is the standard deviation which defines what is the variation or what is the range of distribution in the particle size that you have. Now, this standard deviation, you may have seen that it is just given as one value, but what is the meaning of that standard deviation, one value? Let us say this is some over here we are given some diameter, let us say d is equal to 50 micron, and standard deviation is given as 5 microns. So, what is the meaning of this 5 micron? Does it say that certain fraction of data should lie within this? What is this standard deviation? It is important to know this. So, the importance of this standard deviation is particularly for distributions which have which are called as normal distribution. So, let us say I have, and let me use a few more colors over here to define this in a better way. This is called a normal distribution or a bell curve distribution, because it looks like an inverted bell, and there is a mathematical equation which defines it. It is not just the schematic shape, and you can call anything as a bell curve. So, it is the form, it is of this form, and now this will be it is symmetric in nature with respect to its maxima. So, this is where your maxima lies, and over here if I say this is my mean, so in this particular case mean will be equal to median because it is symmetric, and it will be equal to mode. Now, what is standard deviation? So, let us say there is some value of plus minus 1 standard deviation. It is usually denoted by sigma. So, I am writing it like this, plus 1 sigma and minus 1 sigma. So, what standard deviation defines is that whenever you have a distribution like this, then at least not at least, actually exactly 68.27% of your overall data should lie within this range, plus minus sigma to plus sigma. So, this on the x axis, what do you have here? You do not forget that this is actually a diameter. So, corresponding to this diameter you have some frequency. So, this is describing a distribution, and this is some value. So, this is some diameter. For example, in our previous whatever we took as an example, it was 50 microns, and we also said that 5 micron is the standard deviation. So, this is minus 5 micron and this is plus 5 micron from this mean value, which is usually denoted by mu. So, this for this particular case it will be 50 micron, this will be 45 and this will be 55. So, between 45 to 55 microns you should have 68.27% of your particle size. So, now you see we can get a quantitative feel of how much powder lies, or number, what is the number of powder particles that lie within a particular size range. Once we have this value, standard deviation. So, standard deviation does define the width of distribution. Similarly, you can get minus 2 sigma to plus 2 sigma. So, in this case it since sigma was 5 micron, so this becomes minus 10. So, 50 minus 10, this is 40, and here we will have 50 plus 10. So, 40 to 60. Now, within this range you should have 95.45% of data. So, this is not just arbitrary number, these have been calculated from the form of the equation, and you can predict how much. So, how much data will lie within that. So, for example, let us say z number of sigma we are talking about, then the fraction can be given by ERF z by root 2, and therefore, if you are saying 1, then this is ERF 1 over root 2, which is what comes out to be 0.6827 or 68.27%. When you say z equal to 2, then this comes out 0.9545 and so on. So, you can write keep on going like this by putting in the values appropriately over there. And since we are talking about standard deviation, so let me also quickly say that it is not necessary that you will always get a bell curve or a normal distribution. You may get some random distribution. So, in the what will happen in those cases? This particular equation is valid only and only for this kind of distribution. There may be other symmetric distribution, there may be other beautiful looking distributions, but that is not what this is meant for. It is only meant for this particular form of the distribution, which is called the normal or the bell curve. If you have any other distribution and even a random distribution, there is another way to define the fraction of data that will lie within that, and that is called Chebyshev's inequality. What it says is that if you are within k sigma, then at least 1 minus 1 over k square, at least. Now, remember that is the important word here. Here it was exactly, here it is at least 1 minus 1 over k square data should lie within plus minus 1 sigma. Now, if you put k equal to 1 over here, what you get is 0. Now, that is very surprising. If you go to k equal to 2, you get 3 by 4 or 0.75. If you go to k equal to 3, you get 8 by 9. Okay, other numbers look okay, but what is the meaning of k equal to 1? It says only 0 data lies inside it. That does not make any sense. But then again, if you go back to what I said earlier, that at least this, it is saying at least these many data. So, it is saying that we can, nothing can be predicted about plus minus 1 sigma when distribution is a random distribution. It can have 0 data, it can have lot more than 0 data, but not much can be said. But only when you go to k equal to 2, which is 2 plus minus 2 sigma, then at least 3/4 of the data must lie. So, whatever be the form of the distribution, no matter even if you draw a random distribution on your own, still when you have the mu value, then and you calculate the standard deviation from that, then at least 0.75 or 75% of the data will lie within k minus mu minus sigma to mu plus sigma. So, this is again a very powerful equation or powerful relation which predicts a great deal about the distribution. However, what you would find when we go on is that for the powder that we get from a particular method, most of the time the distribution is what is called as log normal distribution. it's not normal, it's not random, it's log normal distribution. What is log normal distribution? It is similar to normal distribution except that you have to take diameter log of the diameter, and once you plot frequency versus log of diameter, then you would get the usual bell curve. So, we have this log normal distribution. How would it have looked like? If instead of log d we had taken on d, it would have been right skewed. So, you see this is not a normal distribution, and here the axis is d. So, let me draw this x axis over here. So, this is d and not log d. So, when you have log d, this is what the distribution looks like, and when you have d, this is how the distribution looks like. So, here you will not be able to apply the plus minus 1 sigma rules, or basically the whatever the to estimate what fraction of data should fall within that. But if you use the log diameter values, then you can use this value. You can use that relation to find how much fraction of data lies within a given set of with given standard deviation. So, this is what the distribution is, and that is the implication of standard deviation of distribution. So, you can get a lot of information, as you see, when you have the mean and the standard deviation, and particularly when you have a normal distribution. If it were not a normal distribution, there you would see that you will not be able to get a lot more information that we will discuss very soon. Only because in most of the cases, no matter what technique you use, whether you are using atomization or electrolytic technique, the particle size distribution that you get is in most of the cases log normal distribution, and then we can apply some of the results that we will see very soon. Now, this is what a histogram would look like. So, you see this is the particle size, and you can have number over here or weight percent over here. So, it can be frequency or the weight percent. So, you can plot it as on the number basis or on the weight percent or the weight basis. So, there are different ways to plot it. It need not always be on the basis of the number. Other way is to plot on the basis of weight or surface area and so on. And this is the histogram, and corresponding to that you can also draw what is called a cumulative distribution. So, what is cumulative distribution? It is basically adding all the incremental information into the previous data. So, at this point whatever the data was, you add the next from the histogram next set of information into this point, and so on. You can build a curve like this, and this is called a cumulative percent data. So, this is also a very useful way to see how broad the distribution is. Now, here you can even find what is where is the mean. There you can define it as sigma equal to 0, and then you can define sigma equal to -1, sigma equal to +1, and corresponding to that you will have diameter. And another thing is, you see in both of these plots, x axis is in log diameter, because that is when you get the log normal distribution, and you can see it is roughly log normal distribution. If we had a lot more statistics, then it would have been a much more smoother curve, but right now from the data it seems that the statistics is not too large. So, you do not see a very smooth curve over here. It could become very smooth if you have much larger statistics, and this is the corresponding cumulative distribution. Now, if we are talking about cumulative distribution, we should also know that the size, we have already mentioned that size distribution that we plot can be on the basis of number or on the basis of for example weight. So, there are different bases on which you draw the plot. For example, here this is the number basis. So, basically population. So, this is a cumulative plot. Similarly, you can draw a weight basis plot. So, here the weight is increasing as you increase the total number of size. So, the weight of all the particles up to this point is added at this point. At this point you can see all the weights have been added. So, it is 100%. At this particular point 0% of particle size lie, and therefore it has 0% data. So, that is what it is representing, and these two plots are for the same distribution, one on the basis of number and the other on the basis of weight. So, that you have to keep in mind, and these will be displaced. Now, the amount of displacement will depend on what is the particle shape, And why will it depend on the number of particle shape? Because we know the relation. You remember we talked about a relation where we said if n is the number, then n number per unit weight, sorry, not the number per unit weight, but the total number, and W is the weight of that particular mass, then number of particles in that weight is given by pi d cube by 6. Now you see we have assumed here a spherical diameter, a spherical particle. If we had assumed some different size, then this quantity will be different. So this is your weight basis plot, this is your number basis or population basis plot. How much it is shifted is determined by this value, and this value will depend on whether you are taking a spherical particle. If you had a flake, then this will be a very small quantity, it may have a constant thickness, so it will become pi d square by 4 into h. So it will be proportional to 1 over d square instead of 1 over d cube that is over here. So the amount of shift will depend on what particle size you are assuming. Now another thing is that we also need to assume uniform shape of the particles, that we have already mentioned, and again ask your question, is it a reasonable assumption? So we have already made that answer, and the answer was that it is a reasonable assumption as long as you are using the same process to generate the particles. So the same process would give you on average similar shape of the particle size, similar size of the particles. We looked at what is D50. Now similarly you can also determine or define what are D25, D75, D10 and D90. D25 will be the diameter of the particle where 25% lie below this, 75 will be diameter of the particle where 75% lie below it in terms of maybe number or in terms of maybe weight, but whatever it is, it depending on what particular basis you are taking, number basis or weight basis. So you can get a D25, D75. Similarly you can also get D10, D90, other values like this. Why are we interested in this will become very obvious in the next slide. Before that, let us look at, we talked about this cumulative plot. So how would the cumulative plot look like for these different kind of variations? Now you see this is the only normal log normal distribution, other are not log normal distribution. So we would be able to use this particular values or the particular relations that we described over standard deviation only for this one, but not for others. However, cumulative plot we can still find for each and every each one of these. So look at it, try to estimate what should be the cumulative plot for each of these, for a Gaussian distribution, for a polydispersed. So here the distribution is wide, here the distribution is very narrow, here you have bimodal. Bimodal meaning at this point you have a mode, at this point you have a mode. So there are two modes, this is the global mode or the global maxima, here you have a local mode or local maxima. So these kind of distributions, what should be the cumulative frequency plot? You try to draw it on your own and we will reveal the answer in the next lecture. So see you in the next lecture. Thanks.